Okay, so the next part we're going to look at is how to represent conditional probabilities. So far, we just assumed they've been tables. However, there are many different representations that we could use for conditional probabilities and factors. So we can use tables like we did before. We could use decision trees. You could use rules. We can use weighted logical formula. There's something called a noisy OR, which is a useful assumption we're often going to make. There's a logistic function and a neural network. So all of these can be seen as ways to represent conditional probabilities. And these can be used in factors which can be used in belief networks. So there's lots of different ways. So although I've let you think that they're represented as tables, they do not have to be. There's lots of different ways of representing conditional probabilities. So here's the first one. We're going to look at the probability of D given A, B, C. You could write A, B, C, D, and you can tell it's a conditional probability because if you look at the two values here for true and false, they add up to 1. Okay, so if you look at the true values for true and false, they add up to 1. Right, so that's the property of the two, for given any particular values for A, B, and C, the two values for D add up to 1. Okay, so if you look at these tables, you'll see there's lots of sort of structure in here, like this 0.9, this 0.9 is the same, and similarly 0.8 and 0.8 is the same. Okay, so let's look at, so there's representations that we can use to try and exploit this structure. So there's a different representation. This is called the decision tree. So what we're going to do is we're going to look at the probability of D. So this is little d here is D is true, given A, B, and C are the parents of it. And so we can look at the case when A is true, then we're going to look at the case where is B true or false? And if A is true and B is true, the probability of D is 0.9. Okay, so that's exactly the same here. When A is true and B is true, the probability is 0.9. And it doesn't matter what the value of C is. So this is something called context-specific independence. It doesn't matter what the context is. Okay. Okay, so that's the first one here. So when A is true and B is true, we're going to get the same value in here. Okay. Now let's look at when A is false. The probability of, we're only going to split on the probability of C here. So when A is false and C is true, it's going to be 0.3. And when A is false and C is false, it's 0.4. So it turns out so when A is false and C is true, it's 0.3. So when A is false and C is true, it's 0.3. And when A is false and C is false, it's 0.4. And the other values we get from the fact that this adds up to 1. So the fact that, false, true, plus false, true, false, false. When we add these two values for D, we get a 1. So all we need to do to represent, so this represents exactly the same information as this decision tree. So often the decision tree is something that we're going to use in here. So decision trees are very common representations for conditional probability. And it's sort of one of the first representations you'll learn in 340 when we start learning about machine learning. So part of what you do there is, most of the course is really, to me, it's just about learning conditional probabilities. Okay. So another one is a rule representation, where you could say, well, if A and B is true, the probability of D is 0.9. If A is true and not B is true, the probability is 0.2. So let's try and do the same things. When A is true and B is true, it's 0.9. When A is true and B is false, it's 0.2. So there's some people who like to write it in terms of rules, and there's a whole lot of representations that people use where you basically have rules that have weights on them. And you can sort of see this as a similar way to writing down decision trees. Sometimes it's nicer to write down the rules than just to write down a tree. One other way we can do it is, remember when we did CSPs, we looked at this idea of using satisfiability. We tried to map it down into a problem of just logical formulae. And we can do exactly the same thing here. We can write down this as, so this is the case about where A and B are Boolean, and you say, if A is true and B is true, and there's some noise variable, then D is true. So if A is true and B is true, then there's a different noise variable, N2. So it turns out that N1 is a noise variable here that is exactly the same as the probability of D when A and B is true. N1 has a probability of 0.2, which is exactly the probability that D is true when A and not B is true. Okay, so we're going to try to represent this. And it turns out if these can be independent, These noise here can be independent, and this exactly represents exactly the same conditional probability. And so what this does is it lets us use a whole lot of techniques that have been assigned to, being used by the so-called SAT community. People who study satisfiability have used this, and the most efficient algorithms for belief network inference basically use, the most efficient exact inferences essentially use variable elimination or its dual, which is called recursive conditioning, with this representation, because this representation lets us do a whole lot of interesting things, because you can actually exploit a whole lot of structure as well as just tables. Okay, so here's another example of a conditional probability representation. So the robot is wet if it gets wet from rain or coffee or sprinkler or another reason. And they each have a probability of making the robot wet. And this is going to be called what's called a noisy OR, because there's just a whole lot of ways of doing it. If it gets wet from rain, then it's wet. If it gets wet from coffee, then it's wet. If it gets wet from sprinkler, then it's wet. That's why it's called an OR. So it gets wet from sprinkler if it gets wet from rain or coffee or sprinkler or another reason. Okay, so what we're going to do here is we're going to say, well, X depends on here. So think about V1 to VK as sort of rain, coffee, sprinkler, and another reason. And that's the parents of X. And what we're going to do is we're going to translate that into a new network, which has A0, A1, A2, A3, A4. And what we're going to think about this is V1 is like rain, and A1 is like gets wet because of rain. So, and there's a probability associated they get wet because of rain if it's raining. If it's not raining, they don't get wet because of rain. Right? There's this. Think about this as coffee, and A2 is they get wet because they spilled coffee. Someone spilled coffee on them, or they spilled coffee on itself. The robot spilled coffee on itself. And there's a probability that if it has coffee, that it's going to get wet by coffee. Okay, that's what's going to happen here. So what happens is we first of all start with K has Boolean parents V1 to VK, and there are going to be P0 to PK parameters of this. This is what we're going to represent. And what we're going to do is we're going to invent these new variables, A1 to AK, and the probability of A0 is true is just P0. So it's just this parameter here that's A0. And then we're going to have the probability that if VI is true, then the probability AI is true with probability PI. So you're going to think about this as the probability that you get wet is the probability if it's raining, then they'll get wet through rain. Right, so that's what's happening here. That's going to be PI. And if it's not raining, they're not going to get wet from rain. So that's why we can have this 0 here. Okay. And now this is just a real OR. This is just P of X given A1 to AK is an OR. So it's true if one of them is true, and it's only 0 if all of them are false. So that's what's going to happen here. So this probability is now either 0 or 1, because if this is just an OR, but this becomes a noisy OR of V1 to VK with some so-called leak probability. If all of these are false, so there's still some probability of it happening. So this is called a noisy OR. And this is the one that was actually used, in the diagnostic system we looked in Google in the assignment, because if you use the word nut because it's a food, then you use the word nut. So there's a probability of using the word nut if it's a food. There's a probability of using the word nut if you are talking about tools, right? So you're talking about tools and carpentry or something, you have nuts and bolts, so you can talk about nut then. And maybe there's just a random chance that people talk about nuts. But you're going to use, so that's why that has a noisy OR inside it, because what's going to happen is each variable depends on its parents in a noisy OR, because you can use the word nut if you use it because of food, or if you use it because of tools, or you just use it just as random. Okay, so that's what's happening there. So that's a noisy OR is appropriate there. And that's what's used in when we do this topic modeling. Okay. So this is the one we did before. The robot gets wet if it's rain or coffee. It probably gets wet from rain. If it rains, it'll probably get wet from coffee. If it has coffee, it probably gets wet for other reasons. Okay. And so this says the probability of wet from rain if it's raining is 0.3, wet from coffee if it's coffee is 0.2, and wet for other reasons is 0.1. And the robot gets wet if and only if it gets wet from rain, or it gets wet from coffee, or it gets wet from other reasons. And so that's what this noisy or is. Okay. Another one you might have heard of is a logistic function, and often it's presented as sort of just another way to combine values. Let's now convince you that it's actually an interesting thing from probability theory's point of view. So here's this. We're going to start off with Bayes. So just the definition of conditional probability. The probability of H and E is the probability of H and E divided by the probability of E. And so what we're going to do is we can map this out. This is E and H plus the probability of not H, E and H. So these two together form E, and they're exclusive, so I can add them. Okay. And now a good thing to notice is that this is the same on the top and the bottom. So to simplify things, we're going to divide by it. So we're going to divide by the probability of H and E, and we get 1 over 1 plus the probability of not H given E times the probability of H given E. And then we're going to do something very weird. We're going to take E to the log, and just to make it a bit more fun, so E to the log is sort of not doing anything, right? As long as it's everything is sort of, you get, if everything is positive, at least you're going to do this. And all probabilities are all positive, so that's okay. And I'm just going to flip a minus in here, and that's just going to flip this upside down. Okay, so I'm not really doing anything here. I'm just doing this I'm just flipping it upside down. But what happens here is that this is called the sigmoid. The sigmoid is 1 over 1 plus E to the minus X. And this is called the odds. So what happens is the probability of H and E is the sigmoid of the log of odds. So if you see sigmoid, you want to think conditional probability. And the reason we do that is because the odds, this probability of H and E divided by the probability of not H and E, is typically a product of things. It's typically multiplying things. If we take the log, you get a sum. And so we're typically doing the sigmoid of a sum. Often we forget that it's log odds, and often we just think about this as a sum. But if we're really doing this with this way of having the odds as a product. Okay, so here's what sigmoid looks like. It squashes the real line into 0 and 1. So it's going to give an arbitrary real number here is going to be x. The x gets to be here, and it's going to be a probability. It's going to be between 0 and 1. Notice this cannot represent a probability of 0 and a probability of 1, because that would mean that sigmoid has to be plus or minus infinity. Okay, so, and then we typically have a sigmoid of a linear function. Okay. And you might think, well, that can't represent the previous example. In fact, it can represent the previous example as long as we're allowed to put product terms in here. So the probability before of A, B, C, D is, let's put sigmoid to the minus 1 of 0.9. I'm going to write with this funny symbol. So if A and B are true, then I'm going to use this value here, but I'm going to take sigmoid to the minus 1. So that's going to give the probability of D given A and B is true. If A and B are both 1, then this is 1 and the rest is 0. If A is true and B is false, then only this one has a value, and you end up with 0.2 as the probability because this is the inverse. Okay, and so this is a way to represent this, and you can distribute this out into this way of saying this is a linear function but with these product terms. This is also a common term. Often we don't use product terms, but in order to be completely general, we can. Okay, so this is logistic regression. The logistic representation is trying to learn these ones. You'll also learn about logistic regression in 340. So I'm not going to talk about that, how to learn them. Okay, and one other way to do it is just to build a neural network to predict D from A, B, and C. So this is sort of a common, particularly when we have sensing information. So when we have sensing information, when the A, B, and C are very low-level sensing information. The conditioning that a neural network tends to be the most common used now. But we can just think of it as a way to represent conditional probabilities. So a neural network tries to predict expected values. So it tries to get tries to predict essentially the average value. Now, the expected value with a domain of 0 or 1 is its probability. So if you have the expected value of this is 0.9, it means that that's the probability of 0.9. And when we optimize it to mean the probability. So if you see a neural network with just a 0, 1 output, then it's typically trying to learn a probability. And it's typically using the sigmoid activation and optimizing log likelihood. And that's using what we did before. It's using a probability It's trying to predict the probability, with a sigmoid there, but it has its logistic regression model with learned features. Okay, so with the 0-1 domain, it's going to be a logistic regression model with learned features. Is a nice way of thinking about them. For other discrete variables, the expected value is not or real values. The expected value is not a probability, but for discrete values, we can do something interesting. We can create, just like we did for CSPs, we can construct a Boolean 0-1 variable for each value, and it's called the indicator variable, which is true when the variable has that value, in other words, not. And that's basically having the output for each value. So normally in a neural network, that's what we do. We have an output for each value so we can learn a probability. Okay, so and for other domains, a Bayesian neural network can represent the distribution over the outputs, not just the point prediction. So you learn about neural networks in 340, but for us, they're just a representation of a conditional probability, which I think is a nice way to think about them, because it unifies a whole lot of things that we've been looking at before. And a lot of what we've been doing is actually is using neural networks to actually represent some of these conditional probabilities, but we still need to do all the other reasoning we've been doing.